In this video, I'm going to review polar coordinates. You can read about polar coordinates in 10.3 of the Stewart text. Many of you have the second half of the Stewart text, so you can review 10.3 in the WebAssign ebook. In Cartesian coordinates, we define a point as an ordered pair, x, y, and as you know, it's just the perpendicular distances here from the x-axis and the y-axis will give you your point. And that's a unique, the unique values here will determine only one point. Now, moving on to the polar coordinates, we're going to be defining a point this way. First, we've got a polar axis. And that usually lines up with the x-axis. And then we've got O, which we would just call the pole point, which is usually lines up with the origin. And then we have a point P defined not by x, y, but by this r theta. Alright, so you have a counterclockwise angle coming off of the polar axis, theta, and the distance from the pole to P is your r. Alright, so that's going to give you your point in your polar axis. So now, what I want to do is kind of show you, the difference between the Cartesian coordinate plane and the polar coordinates, in which a distinct difference is you've got really this one representation of a point, and for here you can represent a point actually in many different ways. You can represent this one point here as r theta plus 2 pi n. Okay. N is going to be element of the integers. And really what that's stating is that we could go in either clockwise or counterclockwise and end up with the same point, 360 degrees back to this point. And you could also represent this r theta as negative r. Okay, so the negative r would flip this point P down here. But then what you've got to do is really counteract that by moving theta another pi. So let's add actually 2n plus 1, and that's going to give us an odd number here, and pi. Right? Again, n is an element of z. So for example, this point P, which is r theta, can be represented as, if we take this idea, it could be represented as r, same r, and we could just take theta. Let's do an example here. Let's just say this is 5 pi over 4, just for example. So we take that 5 pi over 4, and that can be represented as 5 pi over 4 plus, we'll say n is 1 here, so we'll just say plus 2 pi, right? So it could have been minus 2 pi, it could have been plus 4 pi, and so forth. And then using this idea here, we could say it's negative 5, and then pi over 4 plus, well, you've got, we'll just say n is 1 again, so we'll say 3 pi. And that's going to be equivalent. So these are all could be represented as p. Good. Now, let's kind of look at the connection between our Cartesian and our polar. And you know what? Let's go to the next slide. So here's our xy. And we'll think of a point P. It's going to be r theta, and we want a point P that's equivalent to it, right, in xy. So how do we kind of go back and forth between the two? Well, let's just drop down, get a 90-degree, so a right triangle here. We've got r, y, and theta. And this will be our x value. So we need the connection between x, y, and theta and r, right? So we're just going to use basic trig, right? So we know that sine theta is just going to be y over r. So there's our connection there. And then cosine theta is x over r. And then we can just basically say from there, r is equivalent to, y is equivalent to r sine theta, and x is equivalent to r cosine theta. Good. So these are the two equations. If you have r and theta, you can find your y and your x. Pythagorean theorem going the other way, r squared is just going to be equal to x squared plus y squared. Right? And to get our theta, we know tangent theta is equal to y over x, so you can get theta by the inverse tan y over x. All right. I'm going to think I want to stop there. And I'll talk more about r equals f theta, so these polar functions in the next video.